Thank you everyone for joining this session. It's a great evening. I appreciate for everyone who is interested in learning about efficient convolution neural networks. Okay, so this work has been a group work by me, Sabish Etiraj, who is currently working in Happiest Minds and a PhD student in IIT Jodhpur, Rohit Lal, and also Mohan Kingdom. Okay, so I will take the question answers in the end. And all right, let's get started. Okay. So sorry for being late a bit because the Zoom has started restarted machine and it started updating the software. Okay, cool. So this work, our work has led to 3 publications over the last 1.5 to 2 years, right? So recently we published in Procedia Computer Science. Earlier we published in Springer Conference, efficient deep learning identification of defective casting products. We also did published a paper on augmentations, right? So when we all know augmentations improve the model performance, but when do augmentations work, right? When does they don't work? How just like ResNet, MobileNet. But when you build your own smaller architecture, which augmentations usually work, which doesn't work, which augmentations you can combine. So if you're more interested, you can go and read some of our work here. And if you have any questions, I would be glad to take any of your questions and offline as well. Okay. Coming to the session, so why do we need to tweak the neural networks? We need to get more generally. When we say we are tweaking a bike for efficiency, right? Either for to get more mileage, or if you want something like make it faster, we need to tweak few things, right? I mean, we need to make the bike more lighter, or we need to have more thrust, or we need to have some kind of efficiency in terms of tire diameter and a lot of other stuff, balance, aerodynamics and other stuff. So same way, even for convolution neural networks, you need to tweak the nuts and bolts. So what are those nuts and bolts? Okay, so this talk is mostly why we need to do is because we need to have smaller architectures, because these smaller architectures are very important for specific use cases. I'm not talking about solving problems like ImageNet, and you all know that not the generative AI algorithms, but you have some small specific industrial use cases or healthcare use cases where you need a small algorithm for faster training, for efficiency, and also for smaller model size so that you can deploy on edge devices. Okay, so one of the technique that when we architectural efficiency, right, how we can make the models more robust by data augmentation, and finally we want to improve the generalizability, right, by tweaking optimization, right? So how we are going to see that now. Okay, I'm going to discuss some of our results on both MNIST and CFAR10 because these are some standard data sets, and we also worked on FMNIST as well. These are some of the standard data sets people work on these things. Once we felt that our methods are working good on these small data sets, we applied on real life data sets such as which we used in our 3 papers. In our 3 papers, we use some real life data sets that are available publicly. And we also found that these methods are really helpful on that public data sets because these methods are, we feel like these methods, the combinations of these methods are generalizable. Okay, so one of the technique what we used is depth-wise separable convolution. So what is a depth-wise separable convolution is, so if you have an input size image of 18 by 18 and 3-channel image, right? So normally if you use a 3 by 3 convolution, and what you want is a 10-channel output. So this leads to the number of parameters. So the 3 by 3 is to have 3 filters. So this leads to a 270 parameters, right? So instead of that, depth-wise separable convolutions, I think, have been first used in exception, MobileNet, and even in exception right now. Okay, so when you use depth-wise separable convolution, right, you can achieve the same kind of results with just 57 parameters. So what happens here is instead of multiplying instead of multiplying all the 3 channels, so what you try to do is you apply these, you apply a 3x3 filter on the only one 3x3 filter on all the 3 channels. So that is 27 parameters. And then you still need a 10 channel output. There you expand with the point-wise parameters. This is called the depth-wise separable convolutions. So this will result in 57 parameters. So a 1/4 reduction in the number of parameters. Okay, this has been extensively adopted in the architecture such as mobile net exception and a lot of other newer architectures. Okay, so this is something you can incorporate in your models if you want to if you are building a more convolution neural network from scratch. Okay, and the second thing is you can see that I think everyone is more familiar about VGG architecture, right? If you see the entire VGG architecture, if you see that they have, once you have reached the last layer, if you flatten it, right? So I just want you to focus on this point where you have a 7x7 filter, 7x7, the channel, the last channel size is 7x7, and you have 512 channels. If you have 512 channels and if you flatten it, so it is resulting in 4096 data points. And if you're multiplying with 4096 data points with 2 dense networks, this itself results in 4096 multiplied by 1000 parameter output, right? In ImageNet, this results in 4 million parameter. Okay, so once you reach the last convolution layer and the last channel, and to reach the final softmax layer, you just have 4 million parameter. This 4 million parameter itself is more than the entire VGG16. So what the gains you are getting from the convolution layers, you are losing through the dense network here. So instead of using a dense network here, right? Nowadays, you don't see this kind of thing in any of the architecture. Instead of using a dense network, so what you can do is, so let's say this is your 7x7 feature map, right? What you would do is, instead of that, you can do a global average pooling, just like a max pool. It's just a global, you are averaging all the channel outputs here to one data point. So if you have 4 channels, you will just have 4 dimensional vector. This 4-dimensional vector, like for example here, this will end up with 512 dimensional vector. This 512 dimensional vector you can multiply with 1000 data points, which results in 500,000, right? 500,000. So from 4 million, you are reaching like 500,000. So that itself is a great 1/8 reduction parameters, right? So you can use global average pooling in your custom architectures instead of directly flattening your deep neural network. Okay, and the second thing is, if you want, you can use squeeze and excite. Squeeze and excite is another exciting block where you can use, for example, let's say you have a feature map here, right? So once you have a feature map, you don't know which of these feature maps you are somewhere in the middle layer, right? So once you know, if you know a feature map, you don't know which features you need to feature maps you need to retain, right? Which channels are you wanted to retain. So what would you do is, for that, again, you apply squeeze these feature maps to one-dimensional vector, right? So for example, you have n number of channels, right? C channels here, which is size of H and W, right? You reduce, just like here you did the feature map, you reduce it to one-dimensional data point. So, and you end up with 3-dimensional vector here. And this you multiply with have a small dense network. With this dense network, you are going to again, and with this dense network, we are going to have an output. That output, again, you are going to put this original feature map, and then you will have an output feature map. This output feature map is something like what we see the attention in the natural language processing, the current day attention, right? Instead of using all the feature map output, which you get somewhere in the middle, you are trying to excite some, means you are trying to give attention to some of the feature maps and you are trying to suppress some of the feature maps. So this is the beauty of the squeeze. So wherever you are squeezing to one-dimensional vector, and then you are exciting and you are multiplying that with corresponding vector again, so that these feature maps, important feature maps get excited, unimportant feature maps will get suppressed. So this is one important thing you can add in your part of your network, which will definitely improve your model of architecture. Okay, and then the other thing is called weight space alteration. Okay, This is called stochastic weight averaging. Okay. So with this stochastic weight averaging, so when you're optimizing your training, after 75, I mean, learning rate optimizing is one of the important aspect in getting better generalizability. Okay. So after 75% of the training time, instead of sticking to one set of weights, what you can do is, as you progress in the last 25% of the cycles or epochs, you can average all your network weights. So, and you can update your batch normalization. So this will help in the averaging the weights in the last 25% of the training time during helps you in better generalization, and this significantly improves your model generalizability. Okay, and when your model is able to generalize better, you would get better accuracy. We all heard of Maxpool, right? What does Maxpool do? Maxpool is shift invariant, and also it also helps you reduce the channel size so that you can reach the depth of the network very fast, right? So helps in reducing the channel size, and it reduces the number of parameters required for a convolution neural network. So instead of using Maxpool, right, you can use Blurpool. Blurpool is a recent thing. So instead of directly taking the maximum of all the things, so there will be a small neural network here that would optimize how to average it. So that neural network will again get optimized. So which will you replace the max pool with blur pool. So you have a strided convolution, and you you have a small convolution neural network right here, and then you apply here, and then you get a blur pool. That means you are giving weightage again to the layer here, the values in this particular layer, and you are taking that particular average. Okay, so this is a better option than straightly taking the maximum value, right? It is network invariance to small spatial shift. And we all know that augmentation is an important one, right? So what does cutout do? One of the important important technique that reduces spurious correlation. So what does it do is it removes some of the it removes some patch from your thing here, and it so that when you sky, it thinks that aeroplane is always flying in the blue sky. There are aeroplanes that can go on water, that are landing on the airport. So if you mask out the blue sky, now the focus will be on the aeroplane instead of just a blue sky. So it reduces spurious correlation. So the cutout is one important data augmentation technique. So the other one is mix-up. So in mix-up, what you do is you take two images and you mix them, and you give a probabilistic proportion with which how much you mixed, right? So for example, if you mix the two different values in MNIST, it will result in 3 and 6. This results in this particular top layer. Okay. And the last and another technique that is very useful is label smoothing. Instead of having a hard label as 0 to 10 or 0 to 9, right? You can have a soft labels, and you can achieve these soft labels as like 0.1, 1.2, or 3.1, something like that, by using this alpha parameter. Okay, so that means you don't have any hard labels. For example, if you're training these data points without label smoothing, so you end up like this, right? And validation, it would be like this. That means definitely you are not able to have good separation. But if you train with label smoothing, you will have a better separation on the validation, and your model gets better and better, and it generalizes better. Okay. And another important aspect when it comes to I mean what you call as learning rate, and also, like, for example, gradient descent. Everyone knows about the gradient descent, is where how do you find out the steepest point of your optimization, because that gives you the better loss function, right? Better loss. So how do you know that? How do you reach that loss space where what happens is that loss space should be a wide loss space instead of a sharp loss. Am I audible to everyone? Can you guys just confirm if I'm audible? Okay, cool. So what happens is if you have a sharp loss curve like this, what happens is when you're training here, let's suppose you are here in the training curve. But when it comes to test or validation, a small shift in the data, a small shift in the data parameters of the data will miss you this steep loss curve. You will be somewhere here, right? And you might not have that much loss, right? So instead of that, so this is like just like saying, instead of having a steep 1 meter depth well, you would have a wide range of a wide loss surface, so that even if your test distribution data is slightly shifting, you are not still missing the depth of this loss surface. So the idea here is to make your loss surface as wide as possible, so that even your test data is also stays in that surface itself. So for that, you can use sharpness aware minimization to run your model. Okay, and this also significantly improves your model. Right? And as I told you, learning rate is one of the important parameter, right? So I already told you, right? With better learning rate, you can reach the optimum loss surface. So if you have two learning rate, right, it takes a lot of time for you to train the model. So right, if you have too high learning rate, you would be oscillating between a high loss surface like this. You will, it is very tough to reach the depth, the lowest point of the loss curve. So here, the optimal learning rate is something which we need to determine. So the learning rate should be generally higher in the beginning epochs, and it should decrease as we go down. But there has been a lot of optimization happen there is a learning rate decay, there's a lot of other techniques, but one technique that really helps you in this process is one cycle learning rate. So you train, you first have a step size, you increase your learning rate, again, you decrease your learning rate, right? And you alternate in between the cycles, and you figure out what is the optimum learning rate you should start with. Right? And there are pre-trained, there are such as, you don't need to run this from scratch, you just need to implement, there is one cycle, already PyTorch has already implementation of one cycle learning rate. Okay, so for example, now everyone thinks of MNIST, they create a million parameter model. For a small MNIST like data set, you don't need such a small model. Okay, so for example, what we did was we created a series of architectures on MNIST from scratch. So right, so the first layer here, we first created a 25K parameter model without depth-wise convolution, right? So you start with 8 channel output. From 8 channel, we are reaching 16 channel output. You have max pool, right? And 16 to 32, 32 to 64 at max pool. And finally, we are making it a gap layer, right? As I told you, we are flattening and we are making a gap layer. And we have again a convolution layer, a 1x1 classifier here, right? So and we have a softmax layer, right? So we don't have depth-wise here, but we are using a gap in all the layers. And then we have a 7K parameters, right? In 7K, if you see, we are not going to if you just see that we are not going to 16 channels. From 8, we are slowly increasing to 12. From 12, again, we are using a transpose convolution to 8. Again, from 8 to 16, 16 to 12, right? We are again going, we are not even reaching 16 channels anywhere, right? So this is a 7K, 7,000 parameter, right? So this is a 7,000 parameter, but with depth-wise convolution, right? Here you see we have a depth-wise convolution. So the difference between non-depth-wise and depth-wise is, since we are maintaining the same number of parameters, you can go more deeper, right? So that is, so if you use depth-wise convolution, you can have more layers within the specified parameters. If you go more deeper, as you all know, the more deeper you go, the better the model is, right? Up to a point. So here we are not talking about 100 layers, 150 layers, where you need to use skip connections like ResNet. We are talking about 6 or 8 or 10 max layers. Similarly, again, we reduced to 5K parameters, right? This is without depth-wise. Similarly, this model is with depth-wise 5K. So finally, we created a small model with 1,500 parameters, right? With depth-wise convolution. So now, these are models. So for CIFAR 10, since CIFAR 10 has more complex because it is 3 channels, it has color channels, it has 10, it is the data size is huge, right? And it is more complex because the objects are of different shapes and sizes. So for this, we created a different model called 143K along with 25K, because we are sure that 25K model does perform decently, but a 143K model would be more decent, right? So again, this is the with depth wise, you can see that we have more number of layers, right? We already have 9 layers here, one more extra layer because we have depth wise, okay? And there is a global average pooling layer in all the layers, okay? So now with these created parameters, right? So what we did, so now you can see the results, right? So you can see this shows that whether the architecture has depthwise or not. And this is the accuracy, and this is the latency that you are measuring on a CPU, right? Not on a GPU, but on a CPU. And this is the model size, right? The final model size with the weights. So you can see that you can achieve, right, 98.35 accuracy with just 1500 parameters. And if you can reach 99 with just 5K parameters. You don't need a million parameter model on a small data set like MNIST. On CFAR 10, right, with a 143K model, right, with a depth wise, you can see that here we reached 79.9. With no depth wise, we have 81% accuracy, right? So this is what we did. I mean, this achieving this 1500K parameters with just 1500K parameters is almost like a state-of-the-art architecture that is available here. Okay, and someone is raising a hand. Let me continue my slides, and I will be able to help you guys with respect to your questions. Okay, and so now you can check our inference time as well, right? So we have the least inference time, right? So the inference time is just 2.52 seconds. Okay, so and another important thing is now we talked about several different techniques for optimization, right? For example, we talked about one cycle LR, cutout, blurpool, squeeze and excite, mixup. So we using the same best architecture, right? So we wanted to continue with this 1500K parameter model in MNIST and 143K parameter model in CFAR 10. So when we applied these optimization techniques on these architectures, right? For MNIST, our baseline accuracy is 98.35. Once we applied these techniques, we reached 99.21. That means if you just read 99.21 is what we achieved with 5,000 parameters. So when we applied these techniques on a 1,500K, 1.5K or 1,500 parameter model, we achieved 99.21 accuracy. So if you can check, go and anywhere else, this is one of the state of the architecture with the constraint of lowest number of parameters. And for CFAR 10, we achieved, our gains are much higher. So here we achieved only 0.7% because we already reached the optimum value, right? So, but here our gains are, our baseline model is at 79.9, but by the time we implement Mixup or Blurpool, we have 4 percentage points. You can see that all of these techniques have definitely either stochastic weight averaging, sharpness over minimization, label smoothing. Every technique has improved the model accuracy from the baseline. But the highest technique you got is from Mixup. So the next question we asked is, if we combine these techniques, can we even get a better accuracy? So what we did was, because in MNIST, we didn't get any gains in the accuracy. The reason is, in MNIST, we are already at a saturation point, right? We already reached 99.2. There is not much left for the optimization here. And when you apply these techniques, even the model needs to have some capacity. 1500K parameter model is a very low capacity model. That means the ability to learn more is very, very less. But on CFAR 10, this 143K model, right, 140,000 parameter model, we started with an accuracy of 83.52 with one optimization. From 83.52, when we added these combinations, we reached 86.76, right? And with just 3 combinations, we reached 86.08, right? So, right. So this says that so when you add multiple optimization techniques, so this has the effect of augmenting your model performance even better, right? So we got a 6 percentage points increase from our baseline, right? And when we add all these techniques, okay. So the conclusion on the outline is on MNIST, we had a state-of-the-art accuracy of 19.835 with just 100 parameters. On MNIST, when we add Blurpool, which is an architectural efficiency, yeah, I would share the GitHub URL to the related to this code. Sure, yeah. And a CFAR 10, right? You have 86.76, right? So when you combine this with all these optimizations, okay, and inference time, right, that is definitely directly proportional number of parameters. And the future work, we decrease the training data. We are yet to do this, but we did. We evaluated some of these methods on augmentation. Okay, so this is some of the work what we did, which led to the final 3 papers. Okay, so now I would just walk you through one of the paper which we published recently on the defective casting detection, right? So in this paper, okay, I'm sharing some of these architectures and some of our GitHub link. You can go to my GitHub. You'll find my papers and architectures here. So here we have some metal casting defects, right? So there are 10 different types of metal casting defects. Okay, as you can see it here. Let me expand it a bit more. Right. So if you just see this, right, we applied again Blurpool et al. I'll just show you the final results from this. Okay, so our custom model, right, if you can see it, right, so when we compared, but you always need baselines. So what we did was we compared our models with some of the standard architectures such as like MobileNet, right? Where is that architecture, right? Yeah, so you can see that we combined we evaluated our models on these architectures. Okay, so for example, the MobileNet to detect the defectives, we got an accuracy of on MobileNet. Okay, here, yeah. So for MobileNet, you see we got an accuracy of 86.38%, right? We also evaluated vision transformers. I think that is weight. We got 85.74, right? And for ResNet, we got 70 for whatever the reason it is, and all these are very low. So for Inception, we got 91.48% accuracy. But when we use the same architectures, which are like 590 million parameters, 34 million parameters, 14 million parameters with depthwise and without depthwise, when we did this with 590 parameters with depthwise, we got 81.87% accuracy. This is almost like on par with MobileNet, right? Of course, 5 percentage points still lower, right? So we took this, our best architecture, 590 million, 590K parameter, not even 590 million, it's 590K parameter model. And on top of this, what we did was, we did several augmentations. But what we found was, augmentations generally doesn't work on data sets such as casting. Augmentations do work when your classes are too different, but generally they don't work on when your when your classes are very close. A defect is just a small line of a scratch or some kind of thing. So that the distribution between the defect and the non-defect classes is very, very close, right? So, but if you see, when you are classifying cats versus dogs, the distribution is a bit farther apart. You can easily tell the distribution difference. There, augmentation generally works. But here in our case, where the defects happen on the metal casting products, the distribution difference between the two different classes is very, very less. So in such case, augmentations generally decrease the model performance. This is called as, this is a new finding from our work. We named it as Augmentation Paradox. Okay, you see that all the augmentations have decreased. So it's very much important that you always have baseline in your model to check your model accuracy. So we took the our 590K parameter model, which we got 81.87 accuracy. On top of it, we applied where is that? Yeah, so we took that 81.87% accuracy model depthwise. On top of it, we applied Blurpool and all these things. We got 84% accuracy. And this 84% is accuracy is very close to our mobile net. Okay. And then we evaluated the model inference time. If you see the model inference time on a CPU, we calculated both the batch latency and the individual latency. So if you just take inception as your base, right? We got with our with our custom model of 590K parameters, we got 4 times better lower inference time, right? So if that is even with mobile net, you get only 2 times, right? For example, if mobile net takes 47 milliseconds, our model takes only 33 milliseconds. So that itself is 50% reduction in the inference time, right? So for individual latency, if you don't have a batch, the inference time reduces by 50%. It has 25 milliseconds. Here it takes only 12 milliseconds, right? So either way, our model is it's comparable with the mobile net accuracy, and also on the inference time, and also the parameter ratio. So parameter ratio for mobile net, you have 3.5 million parameters, but our model is just 590K. So which is like 1/7 of 1/6 or 1/8 of a mobile net architecture. With a 1/8 reduction is in parameters and 50% reduction in inference time, our model with the optimization is much better and comparable to mobile net. So here, what we did was, first we evaluated on architectures such as CIFAR10 and MNIST. Once we felt confident that we can replicate this, we took some real life data sets that are industrial data sets, and we applied these techniques on this. And this is a data set, and this paper is also publicly available. If you are interested, you can share this. You can check my Google Scholar as well for this paper. Okay. So, and to achieve these things in our thing, we used a library called as Mosaic ML. We should give a lot of credit to this library, because this is the library. Once we created our custom architectures, we use this library called Mosaic ML Composer, and it has a lot of methods. We use the methods because this is a library that they are creating optimizing neural networks. So from this library, we took some of the things such as right, the Mixup, label smoothing. Of course, there are these techniques and these library add-ons or packages are available outside as well. But it is very useful for us. Like, for example, if all these techniques are being in one, optimization techniques are in one place. So we took the advantage of this library. So for example, the squeeze and excitation, stochastic depth, sharpness aware minimization, Mixup, okay, label smoothing, layer freezing, right? So whatever that is applicable to our architecture, our models for convolution neural networks, we took those and we put these on top of our models, and that definitely improved our model metric and model Blurpool, Upmix, right, and Cutout, right, on our architectures, right. So this is, you can also please feel free to explore this. This is an open source library, and this has helped us achieving some of the state-of-the-art results on our architectures. Okay. And coming back to our augmentations paper. So we all know augmentations are generally good, but most researchers have focused on applying augmentations to large neural networks, such as millions of parameters like mobile net, ResNet, but our focus is on smaller neural networks. So what we are trying to do is to evaluate the relationship between model capacity and augmentation. That means if the model capacity is going down, so the same augmentation can have the same effect, or which augmentations are generally better even if the model capacity is going down, right? So also, what is the effect of multiple augmentations on the model capacity, right? So and finally, the augmentations effect on depth-wise separable convolution. What effect do you get on depth-wise separable convolution? So we created a set of experiments. Again, we took CIFAR10 and CIFAR10 here, and also FMNIST, because we did MNIST only one model, but we didn't focus much because MNIST is a too easy and too optimized data set. But fashion MNIST is something, it's not an easy data set to crack. Why? Because I'll just show you the maximum accuracy so far achieved on fashion MNIST is 98%. So we created these small architectures of from 1500 parameters to 600,000 parameters models with both the depth-wise and non-depth-wise. And we applied these models with variety of augmentations, like for example, flip, rotate, random perspective, cutout, mix-up, random affine, and color jitter. And we applied on these three data sets with various number of architectures. So now, if you just see that, right, for example, there is this random rotation. On FMNIST, you get 90% accuracy on FMNIST on a 5.7K architecture. But if you use 600K architecture, you're getting 94, right? So definitely, what does it tell, right? So the baseline is 94.19 and without the augmentation, but with the augmentation, you're getting 94.39. Here, that means this thing is not actually helping you a lot. Okay, so you always need to compare with respect to the baseline. So when you see this, what is our inference is on FMNIST and anywhere. So our inference tells us that how much percentage efficiency you got. Okay, so what our idea is, your augmentation technique should have a consistent augmentation. So now the augmentation should have a good effect on as you increase the model capacity. So for example, Cutout doesn't work on smaller data sets. See, Cutout only works on huge, but if you have a better model, only Cutout works. But there is one model that is always performing almost better, is on CIFAR 10, right? Especially if you see on CIFAR 10, Cutout and so even on the smaller architecture, Cutout and Mixup, right, are giving better accuracy, right? And random affine is even getting better accuracy. So the augmentation techniques has different effects on different data sets. Okay, so and which thing is better, we just outlined in this paper. I don't want to discuss too much of this paper now, but we also told that which augmentations are generally synergistic, which augmentations generally antagonistic, right? So sometimes you combine two augmentations, they perform better. Sometimes if I combine two augmentations, they might not perform better. So you need to be very careful when you combine two augmentations. So the take-home message is, right, what I wanted to show you here in this, right, the take-home message is on FMNIST, right? If you see on an FMNIST data, right, this is an FMNIST, right, with a 6, the best accuracy what we got here on FMNIST is 94.92, right, with a 600K parameter. If you see, this is one of the SOTA accuracy what we got with the lowest number of model. If you just go and check FMNIST, right, these people created a fashion MNIST, and right, if you see the accuracy of on fashion MNIST, right, only huge models, right, huge models with 5 parameters, right? For example, this got 94%, all right? You can see that 95%, but this is a huge parameter model. Yes?
Sorry to interrupt. I was request the attendees to please fill up the form.
Yes, yeah.
Feedback as it helps us to conduct more sessions.
Okay, sure. Right. So feel free to go through these architectures, and some of my papers are available on ResearchGate as well. If you go and check my ResearchGate profile, all my papers are available on the ResearchGate as well. And I shared my GitHub link as well. I will share this PPT once I'm done with this presentation. Okay. With this, I would like to stop, and I would like to take your feedback, and I'm ending my presentation today.
Yeah, first question is forensic data analysis on stack multiply fingerprints on the same spot on exterior surfaces with the use of convolution image ETL possible to do?
I mean, this looks like I have never worked on forensic data. Okay. On stack, I am not able to understand what is stack multiple fingerprints is. Possibly I need more information on how to understand this data set and this task as well. Okay, so I feel like I'm not I don't have enough experience in this particular area to answer this question. Do you have to test all or most of these architectures on various data systems are the most appropriate ones to use? See, it depends, right? So if we have a 340K, we already released all these architectures in public. I see for tiny object detection on aerial images, I'm really not sure what is the best. You see, most of the time, deep learning is test and try approach. You need to test your models and then you need to decide it. So we already created these architectures for people to experiment. And you can take use of the Mosaic ML to for any of the optimizations. And whether if you want George's question, whether if you want to test most of these architectures, I mean, it's better to test and decide which one is best for you. And if you want, you can take our architectures in the way you want, if you have more ideas and more optimization things. So unfortunately, this is a work that's been at a very low level. That means it's not a very high level talk. Sure, I would be open on LinkedIn. I would be glad to accept any request and we can discuss. My GitHub link I shared, you can find the papers and the GitHub link, some of the codes that for our papers as well here. All right, thank you very much. Thanks for the opportunity.